Okay.
Sure.
I'll take over now. So
Thank you.
thanks everybody for coming over the weekend. And so my topic will be toying with neural model of algorithmic trading. It's a very broad topic. And so my take today is to give you a very broad context so that you can I think somebody is making noises. So maybe you guys should just mute your speakers. Okay, and so
Okay, let me mute all, so you can unmute yourself probably. Let me do it. Okay, let me mute my.
Okay, so okay, can you guys still hear me? Okay, I think so. All right, so can you see the screen? Okay, so the outline is we have three topics to cover. The first one is I'm going to introduce the context, why we are doing this, motivation, and the basic topology of the system. And the second topic is the actual model, the model research part, and the computation involved. How do you scale up your computation for the model research purpose? And the final part is practical, the trading system. How do you implement your model, and how do you organize the whole end-to-end workflow so that it's more efficient? So between each of the sections, I'm going to have a small break, and you can ask questions, and we can have free form discussions. Okay, so I'm going to start with the first part. All right, so the landscape. So this is a very high-level overview. There are many players in this particular industry, arithmetic trading. Many different players, such as informed players. Those include hedge fund traders who either have insider information or they have strong forecast. So they have alpha. That's why we call them informed traders. So the other big part is uninformed traders, such that people trading randomly or maybe turnover of the portfolio. And then there's big market makers. Market makers are very essential participant on the system. So let me just draw you some quick graph here. Right, so you have those informed player, right? For example, hedge fund, right? So you have those uninformed traders, and then you have market maker. So there actually overlap between market maker and the informed traders because obviously market maker, they do have information advantage. So first of all, they see the order flow among various participants. And also they also employ somewhat advanced machinery for forecasting of the prices and the volume. So they do have a certain overlap here. So let me just give you a basic like story of how the thing fits together. Right. So let's say informed trader, let's say there's some discretionary researcher who believe Microsoft good stock is going to rise in the next month also. So he will have somebody, usually it's execution desk or external execution trader, to buy Microsoft, right? And during the buying process, the market maker usually acts as a counterparty, right? So basically, market maker will try to sell their own inventory, Microsoft positions, and sooner or later, the market information will, the information from the involving market will transmit back to market maker. So at a certain stage, the market maker will become aware there's new information as somebody is going to buy a lot of Microsoft stock. So the market maker will act differently. Hence, we say market maker usually also have information advantage here. And on the background, right, we have different people buy and sell stock. Those are all random traders like you and us. And there is also might be uninformed proprietary trader who think they have information advantage, but they don't, right? So information is equivalent to alpha or signal. They are interexchangeable. Okay, so that's the first part. So the second part is that the market is very complex, right? It has spatial and temporal dynamics. By spatial, I mean there's different exchanges. They are located usually at different geographic locations, where there's certain relationship between different exchanges, where there are arbitrage relationship, or the future market versus the equity market. And then there's temporal dynamics, right? What I mean by temporal dynamics is there's big orders sometimes here and there, right? Big orders to buy, maybe big orders to sell, right? They don't match with each other, right? They come at a random time. So, and market maker will sometimes take advantage of temporal dynamics to transfer risk from one time to the next moment. So the market maker sometimes acts as a risk transfer or risk bearer. So it's a pretty complex situation here. And okay, so next one is actually what? Sorry, let me just clear my graph here. All right, so that's just a very basic introduction, and next slide is what's the motivation here. So why we are doing this. So obviously, if we are trying to trade in this market, trying to come up with new model, it's for the obvious reason, maybe it can make some money. But what's the fundamental question of why there's a profit to be taken, right? So there are two very opposite explanation. So at one end of the spectrum is that sometimes people think they are doing a very essential service, is to help the market do a better functionality in terms of price discovery. And then some other camps would think algorithmic traders, they are just a predatory front runner that basically prey upon people who are slower. So each of them have some merits. So I won't go into the controversial opinions, which one is right or not. But basically what's really happening here is that for all the arithmetic traders, in order to make a living, they have to have certain advantage in terms of alpha discovery and in terms of prediction. Right, so let's go to the next page here. So what's a typical setup, right? So when somebody asks you maybe to build some new model to trade in the market, usually they will give you market data, historical capture market data, right? So those are really most likely exchange captures, meaning those data are directly captured off the market data feed, right? So probably some of you are familiar with the feed, but in general, those are just like text or binary dump, right, of the trade price, right? Those have the bid, ask, and other informations here. That's at a very, very coarse level. And usually what you need to be doing is actually you need to forecast something out of this piece of very messy data. So your role is to find relationship that your algorithm can exploit. So this is basically the model building process. Right? We're going to come back to how do you do this like in exact fashion, but this is just a typical setup is actually very simple. You are giving a piece of data, you're going to find some relationship. So the first one is the first very important question you're going to ask yourself is what exactly are you trying to predict? So at a minimum, right? You can probably answer. Sorry. Right. So the price is definitely something that is obvious to everybody's mind, right? So but sometimes it's not enough, right? So you have to really give a very precise definition of what you're trying to achieve. So you maybe say, okay, I'm trying to predict the price at a future time, maybe price after a few minutes, maybe after a few hours. So those are choices, and then somebody will actually come in with a different measure. Maybe it's price divided by the volatility of the stock, right? So that's also a reasonable thing to predict, and this is important, right? Because if you're going to predict a price at a certain horizon, you're going to have to precisely define and how do you choose those horizons. So let me go to the next page here. Right, so the choices forecasting horizon is very important. There are many considerations here. Right, so if you pick a very long horizon, let's say you pick a horizon of 1 day, right? So that means you do have, maybe you have 1 year or 2 years of historical market data, right? And if you are trying to predict the price in the next day or after 1 day, right, you are going to have a lot of overlapping data, right? Because let's say this is 1 day's data. This is next day's data, right? Let's say this is 10 o'clock today. Maybe you are trying to predict 10 o'clock tomorrow, right? You're trying to see the price after 1 day's evolution. And the longer horizon you have, the much overlapping you have actually against your underlying data, right? Let's compare this 1 day to, let's say, 1 minute, right? When you have 1 minute, you actually have a lot of independent data, right? Every day you have hundreds of minutes, and those are actually independent data. But if you are choosing 1 day, you actually you can construct same set of pairs, but those pairs, they do have correlation. So this particular relationship is very similar to another adjacent pair of information. So typically people will try to find a sweet spot, right? Maybe several minutes. Let's just say let's have 5 minutes, right? Maybe because your model is very strong in this short horizon, or maybe you have a infrastructure that will not enable you to do 1 minute trading, but will enable you to do 5 minutes trading. So those are different trade-offs. But what's critical is that you find your sweet spot, right? You find your sweet spot, and that's not only because of the model, but also because all the constraints you have in the setup of the system. Right, so I will let you have a discussion shortly, maybe after another couple of slides. So all right, so once you have nailed the forecast horizon, we also need to think about what are the horizon in terms of look back. So what are we trying to achieve? Are we trying to achieve, maybe we're going to use the past week's information to predict the next 5 minutes? Or are we trying to use the past 1 year's data to predict the next 5 minutes. Right, so those are this is actually a lot of domain knowledge is involved, right? Because not only you have to choose your look-back horizon, right? You have to also to decide, are you going to treat all the data in this look-back horizon, these big blocks? Are you going to treat all the data in the same fashion, uniformly speaking? Or are you going to sample this data so that in the look-back window is going to be more relating to what you are going to expect in the next 5 minutes, right? For example, let's say maybe you are more interested in all the time at 10 o'clock in last year, right? You probably don't really care about like 3 p.m. So I mean, if that's your model, maybe you want to filter out all the information just to that particular time slice, right? So this is called panel. If you are going to panel regression, but this is similar. So you're going to pick panels. Right. So basically, you have many choices here. You have panel, right? Or you can pick blocks, right? And or if you have more advanced, you're going to have sieves, right? You're going to have very fine control in terms of how you carve out historical data, so that those pieces of data is mostly relevant to the next 5 minutes. So the look-back horizon is a very skilled consideration that you have to think very carefully. All right, so Sean, can you unmute? So maybe that's the first part. I think I just gave you a very high-level introduction. So let me see if anybody have questions, and we can go into a discussion.
Okay. So anybody, any question?
So I think we're trying to arrange this so it's more of a like free form discussion. Like it's more interactive here.
Yeah, just imagine we are at a round table. Everybody is drinking tea or drinking wine, whatever. It's like conversation here. I guess everybody just wants to meet, right now you probably don't have.
Okay, it probably is too early. So is anybody here like involved in like equity trading or arithmetic trading or trading in general here?
No trading experience.
I think it's now the AI trading, right? Now you don't need like AI. AI is everything now.
Right, we're going to go into the AR part later. Okay, so let me just go to the next section here, and then we can always come back to this discussion. So do you guys actually can you guys see the see my drawings here?
Yeah, very good, very good.
Okay, maybe can you mute everybody again? All right, thank you. I think I unmuted myself. Thank you. All right, so just bear with me here. I got to constantly switch between the mouse and the drawing here. All right, so let me just let me actually clear the drawings here. All right, so I think the next one is the meat of the whole chapter here is that we're going to talk about the model itself, and also how do we employ advanced machinery. For example, AWS, how do we compute at really large scale? So as everybody knows, the model part is very intensive in terms of computation. So we're talking about neural model here. So basically, those are neural networking. Those can be many deep levels, or those can be very shallow, maybe like a couple of levels. So in general, the neural model is much more powerful it's also performing well if you have a lot of data. So in finance, I think we do have a lot of data. And I think we have also reasonably structured data. In this industry, they also have unstructured data, right? They call this alternative data. Those including news, including research report. They may also include in like earnings transcript. So those are a lot of data that you can extract sentiments, and those are primarily NLP, natural language processing machinery involved. But what I'm going to concentrate here, we're going to use neural models just primarily for those structured data. Right? By structured, I mean once you have market data capture, once you have historic data, right? You have bid and ask, you have maybe order book, you have the trades. So how do you just base your forecast and base your alpha prediction process on those structured technical data? So usually they call this historical technical data. All right. So and also, so why are we using the neural network here? So firstly, it's just for curiosity, right? This is a very very hot topic, and neural model has proven itself to be extremely useful in terms of computer vision and in terms of speech, and in general in terms of those very hot hierarchical pattern recognition. So in terms of trading here, trading is a very complex time series. It involves a lot of instruments. It involves at very fine time resolutions. And there are certain technical, analytical people who seems to be performing better than uninformed trader. And a certain discretionary trader seems to be able to inspect pattern visually and take advantage of what they think is intuitively the intuitively right trade, right kind of trade. So people have long been speculating that the machine can do a much better job. That remains to be seen, but I think it's reasonable that neural model to be employed. And so neural model is based on non-linear model here. And if you configure the network to be very simple, straight in, straight out, then the neural model will degenerate into traditional linear regression model. So in that sense, right, if you configure your network, if you drive your parameter into a degenerated fashion, you will be able to simulate the linear model, which will provide as a benchmark. So that's the motivation of use neural model. Let me just also give a very brief introduction, right? What is neural model, right? Neural model are basically you have a lot of input. Let's say 4 input, right? You are going to have intermediate nodes, right? Those are biological equivalent of neurons, right? So, and you can have different topology of connection here, and usually it involves several levels, right, of connectivity, and then it will finally give you some output here. So what we actually accomplish here, we're trying to net the final output, output a specific number, right? We're trying to forecast the price in next 5 minutes. So this is a numeric output. In certain other neural model, right? In terms of maybe there's classification model, which will not give you a final numeric output. However, it will give you label, maybe it'll give you 3 label, maybe it'll give you buy, sell, or do nothing. Right? That's also impossible. That's also possible. However, in terms of the, let's say, futures trading or equities trading, I think the numeric output is reasonable, because that's actually if you are trying to do a 5-minute trading, it's pretty active, right? So it's not really like the CTA style trading that you're going to buy and you're going to hold it for a long time. Okay, so that's a very short introduction here. Okay, let me try to clear my drawing here and move to the next slide. Okay, so basically once we know we're going to use, let's say, neural network, what tools are we going to use, right? So this is a very typical question for people like us, like who are very into developing. So I think the tools is actually not that it's actually pretty straightforward, right? So what I used is basically I use Keras, right? This is the this has neural network built inside, and this is a Python friendly module. It's built on top of TensorFlow. And TensorFlow is what Google is championing for most of the Google's artificial intelligence and Google's machine learning. So the TensorFlow itself is a finely tuned library based on hardware accelerated architecture, right? Usually it's been underpinned by GPU, and this is mostly NVIDIA, right? These are primarily for acceleration for the model training. Lately, it also has, the NVIDIA has also been venturing into the field of inference, right? So we have two distinguished here. When we say about training, it's going to train the model, tune the parameter, right? Find which network architecture is best for the problem. Once training is finished, right? Once the training is finished, the model is fixed, right? You know all the parameters of each of the neural, right? Then you're going to put this into production. You're going to feed input here. You're going to get output here, which are predictions here. And this is called inference, right? So, so you can actually employ very similar architecture for both the training and the inference. So typically training is very compute intensive, and typically the inference side, especially if you're talking about trading, the inference side is more focused on producing low latency result and also supporting high bandwidth inquiries. So most of my code is actually directly using Keras, right? Well, so basically this is your Python codes here. Right. So once you build your Python model, you're going to take it to training. You're going to finalize your parameters, right? You're going to download your model. So you're going to export your model, right? You can download your model into the inference engine, and that completes the whole process here. Okay, so that's a typical setup, and I think for most of the developers, you actually find it's much easier than we initially anticipate. So certainly, once you pass the configuration in the environment, this is actually a much easier setup to work with, like compared to, let's say, iOS development, or even compared to maybe a website. So in terms of tool set, is actually pretty easy. I think I missed one thing here is that I also missed the part of visualization, right? So I think nowadays visualization is very important because we are talking about very complex data relationship. We're also talking about you have to use visualization to validate if something is good or appealing. So so what I use, and different people have their own personal choices here. What I use is actually a typical spot file. And I think people can also just do the visualization inside the Python, which I do as well. And I used to be doing visualization inside MATLAB, and I think everybody has their own choices here. What I find appealing regarding the typical spot file is that it handles timestamp pretty well. It handles timestamp up to millisecond, and so for high frequency trader, right? For high frequency trader who cares about seconds, milliseconds, that's pretty necessary requirements here. All right, that's about the tools and platform. So let me just go to the next one. Okay, I'm going to clear my joins here. I think we touched a little bit about the neural networks here. I'm just going to give you a very simple layout, right? So I think we have this big piece of historical data, and we have all the time series, right? Let's say, right? Let's say you have a time series come out, right? You have many different time series, right? Let's say this is your price. This is the trade volume, right? And a bunch of others, right? So and what you need to predict is, let's say, the price in next 5 minutes. Let's take a very extreme case. Let's say you're going to just predict one single time series. You shall see later that it really doesn't matter that much, like between one time series or multiple time series, as you structure this correctly. The first step is, regarding time series, we always want to have the time series bucketized, right? So basically, let's say you're going to have a interval of, let's say, 2 seconds, right? So you break down your time series into 2 seconds. For every second, you're going to sample the time series. Maybe it's average, maybe it's the first opening value. For volume, maybe it's aggregation, right, within this time intervals. So you're going to have this big matrix, right? You're going to have a matrix here, right? This is time, and this is different channel, right? So how do you hook up this to a neural network, right? So extreme simple layout would be, let me change the color here, right? You are trying to say this is the time, and this is the price delta t, right? Let's say you have a network which is connecting to every node of the matrix into this node, right? Maybe you have another node here, another nodes, right? So this is the first level. I'm just giving example. Maybe in practice, maybe you have a lot of those here. Then the second one, you're going to have another. So I'm drawing here as if everything is connected to everything, like between successive layers. And now you have the final nodes, right, which is going to predict the price. And so this is basically your X, right? Which is a matrix, which is, let's say first one is time, second one is channel. Number of channel, number of snapshots in the time horizon. Let's say you have 1, 2, 3, 4, 5 snapshots, which means you're going to look only at the past 5 intervals. Then this equals 5, right? And in this particular example, you only have 1 price and 1 volume. So the channel is 2, right? So basically, you are going to connect this matrix here with this network, and this is your Y, right? So if you just look at this graph here, so it looks pretty messy, but if you actually go and play with some example keras model, some Python example, it actually is pretty straightforward here. I mean, later I can, after demo, after presentation, I can show you exactly what I meant. But in terms of implementation, those are approximately 20, 30 lines of code if you're using keras. Right, so this is showing a very basic layout. Okay, going back to what I said in the previous slide, that if you make this network simple enough, it's going to be equivalent to a linear regression, right? So if you be extreme, right, if you just take one node and connect to everything, that's essentially a very much like a linear model. Okay, so I think that's just to give you an example here, and let's go to the next slide. Actually, I think this section is pretty intensive, so maybe I'll stop in the middle here, and let's see if you've got any questions here. Hey, Sean, can you unmute everybody? So I think maybe everybody except that you are about to speak, maybe you should mute yourself and unmute yourself only that you are going to speak.
I hand over the control to you, so you can do whatever you want.
Okay, I'm not familiar with this, but all right.
Yeah, I can mute myself.
All right, so has anybody got questions? Because I think this section.
I have one question for you.
Sure.
How do you training the neural network? How you there are a lot of data to training, right? The history data training, connections, the weights, right? Those network are weights.
Right. So yeah, let me first unmute over here. Sorry. Sean, okay, you have unmuted. Okay, right. So the question is about how do we actually train the network? The training is pretty standard. Once you config the hierarchy, once you config the topology of the network structure, you're going to feed with your X, you're going to feed with your Y. You're also going to specify the split, right, between your training data and your validation data, right? You may also have to determine, there are several parameters that you have to give it to the system, right? There's just learning rate, which determines how fast or how big a jump you're going to make after each step. There's also, you have to determine the epochs, right? How many laps or how many rounds of training, sorry, how many rounds of training you are going to go through the data set, like how many times you're going to go through the data set. So those are parameters that are actually very difficult to tune. So I'm going to talk about this a little bit later, but to summarize, the training is pretty standard and you have to tune a number of parameters. And in terms of the theoretical aspect, right? How do neural network learn the weights? That's mostly relying on the classic bike propagation, right? So what does it mean that it will compare, so it will first give some random parameters, random weights to all the connections, right? It will try to calculate a output. It will try to compute the difference between the calculated output against that of the benchmark, right? And based on the difference, is trying to calibrate the parameters, right? So analogy, think about in the old days how people, they're making electronic circuits, right? They're trying to tune into a certain AM radio station, right? They're going to tinkle the resistors, transistors here and there. So let me actually mute everybody. So Sha, I don't think I can mute everybody here, but maybe you wanna mute everybody here.
Yeah, I muted everybody.
Okay. So basically, you're going to tune up your, let's say, your resistors, your circuits like manually, so that you can get the best quality of the radio station, right? So you're going to do something very similar here, but it's more algorithmically. All right. So that, but ultimately, it's about matrix multiplication, calculate the difference, relate back the difference, propagating down level by level, and make adjustments. It's standard, and we can talk about the detailed press later. All right, so maybe I'll go to the next one. Right, so I think some of you who probably have more knowledge about the neural network is that you're probably very familiar, or you're probably somewhat heard of the CNN, convoluted neural network. So those are primarily used in vision processing, audio, signal processing. And it proves itself to be also quite useful in terms of the price forecasting, right? So what does it mean here is that, okay, let me clear the drawings first. Right, so let's say you have very similar patterns, right? Which I'm just give a very idealized pattern here, but let's say system is going to try to pick up this pattern here, and the system trying to pick up the patterns here, right? And then you can use something called a convoluted neural network, which is basically saying that you are going to have the kernel, which is a series of neurons. Let's say you have 4 neurons, right? Collect the big matrix here, which is the same matrix we just talked about in last slide. And you're going to have the same set of neurons here, right? This is that piece of big matrix. It's connecting to the labeling blocks, and you're going to repeat these structures one by one. So the advantage of this hierarchical structure, repeated structure, is that it's going to reduce the parameter set. Let's say you reduce parameter set from many millions, maybe down to a couple millions, just because you're going to have those weights, right, to be same across the board. So the weights has to be same here. The weights has to be the same here, right? When I talk about weights, I mean here actually. So I think this is a little more advanced, but I think it's if you have time, you can check out CNN, and CNN is a very fascinating topic. The idea is very similar to the human V1 visual processing vortex. It's actually a very similar output from the human brains here. Right. So, but in terms of the output, let's say, right, in terms of the output, let's say this kernel is very specific. It's trying to detect a surge in price and the volume, and they are hyping temporariness, meaning when the price is surging, the volume is surging, right? So it really doesn't matter if the price surging happens here or the price volume surging happens here, right? It's going to be picked up by here or by here, right? And usually they have another layers here, which is called the pooling layer, right? Which is going to say, okay, the price has surged. So it's hierarchical structure, but it's very important. So this is a little bit advanced. I'll just go through this quickly. All right, the next one is feature engineering. So feature engineering is actually depends mainly on domain knowledge, right? So if you are a discretionary trader, and in the past you have been observing something that you think is useful, you can translate your ideas into specific formula, right? You can pre-compute those features. Let's say you observe some pattern, which is basically you observed. All right, so let me just say. Right, so let's say you observed maybe the morning, the first 5 minutes, right, from 9:30 to 9:35. Right, maybe you observed some ETFs or the certain particularity about the CTFs, right? So then you can pre-compute. You can give all your knowledge. You can pre-compute some of the derived features, right? And then you can actually insert those derived features into the big matrix we just talked about, right? So those structures are flexible in that you can manual engineering new factors. You can augment your technical X with derived features that you are going to cook up yourself. Okay, so that's a very brief introduction of feature engineering. But feature engineering is a big topic, but it's really domain specific. All right, we're going to talk about another consideration is that maybe your model is not depend on time of day. Maybe your model makes forecast regardless if it's 1 o'clock or 2 o'clock, right? Or maybe your model does care about 1 o'clock versus 2 o'clock. So these are more advanced subject. But if you're going to be using intraday, if you're going to use intraday specificity model, then the neural network has to reflect the fact, right? So there are two ways to go about this. So first one, you are going to make some flag, right? You're going to maybe have additional X, which specify this is at what time of day. That's one way to do it. The other extreme is that maybe for each time interval, maybe so for every half an hour, right? You're going to build a model, right? So you have a different model for 1 o'clock and different model for 2 o'clock, right? You're going to have a smoothing interpolation, right? Trying to take the output from the 1 o'clock model, take the output from 2 o'clock model, and interpolate the result, and use that for your trading. So that's additional thought you have to put into the system. So I'm going to skip this. Is anybody trying to say something? Okay, let me go over here. All right, so next one is also a very broad concept, right? Like how do you go about to find out the best network architecture, right? So this is right. How do you go about? Do you do something like or do you have more layers, right? So you have a lot of freedom. You have a number of layers, right? You have a number of nodes in each layers, right? And then you have also many advanced artificial nodes, such as you can also apply dropouts, which is a technique for regularization, right? You can also apply batch normalization, right? And for the layers, right? You're gonna how many CNN layers, and for each of the CNN layers, what is the kernel? So a lot of different things to consider. What I'm trying to address here is that because we are all software developer, and many of us really think about how we scale our problem solving approach, right? The way I thought about this is that we have to make the architecture flexible, and the architecture should be able to explore on its own, right? So what I consider a good approach is that you're going to have all those different aspects of the system coded, right, into some of the meta parameters, right? So let me give you an example, right? So if you're going to code all those, right, into maybe a structure, right, and let's say your structure, when one member of the structure flip, let's say from 0 to 2, right? You're going to have a totally different group of architecture to be realized. So I think the key is trying to, in order to scale, right? You're trying to code your program in such a flexible way that instead of you are going to try to manually explore all the options here, you are actually going to have the program mutate or have the program randomized and explore on its own. This is similar concept that Google is doing with its own auto ML, which stands for auto machine learning, based on very similar concepts. But for every developer, I think you always come up with something that is really user friendly, so we can code this up in a friendly way, and then we can scale the operation and just have one simple command and run a lot of options here. All right, so that's architecture. All right, I think it's I'm going to skip this one. I just go talk quickly about where the fitting process is usually you're going to train your parameters. A lot of times you're actually going to overfit because the neural network is really very powerful, right? It's really trying to memorize all the input data. So you do have the phenomenon of overfitting, right? So when you have overfitting, you're going to solve it usually by regularization, right? Usually by dumb down the network a little bit. As I mentioned in the previous slide, you have dropout features, right? But you can also apply specific regularization term by inserting those terms into your optimization target. All right, so that's a basic way to address an overfit. More important is that you need to have a lot of variation, try a lot of different approach, a lot of architecture. You really need to have a very diverse group of models, right? And ultimately the goal is you are going to have a lot of different models, right? And you have to put all those models together. That achieve two purposes, right? So basically it's going to have the a group of model vote for the final solution. It's going to address the overfit problem because each of the models, they are slightly different, right? They are somewhat independent. So the diversity is actually one of the cure for the overfitting. But also because the in sample you have a group model, and then typically one for the model, like when you involve one for the model, you can involve this particular model independently from other models. All right, so I think I already touched a little bit about the hypertuning. So basically, hypertuning is the process I talked about previously, that you have a lot of parameters to tune for the training, right? You also have to search different architectural structures, right? So how do you do this? As I mentioned the previous one, you really have to code your program, right? Make a certain structure, right? And for each of the structure, you randomize it. And for each configuration, you are going to distribute into a virtual machine, right? So how do you do this? So you can do this a number of different ways. You can construct your own cluster for machine, but what I find to be very easy is actually you can use AWS. You can spin up a relatively small cluster. Then you can either run. There's something called Spark, right? But for this one, you don't really need a complex system Spark. You can actually just run your own distribution scripts, right? So you can just run your own map reduce process, right? You mean each virtual machine is going to handle a specific parameter set. Right? Reduction is the once it has the result, different virtual machines write to a centralized database, right? And then you're going to have the database output, the final result. So the hypertuning is really a compute intensive process. Okay. So I think compute at scale, I think that's basically the same thing here. I think it's particular emphasis here that the computation, the scalability of the computation is as much as important as the sophistication of the model, right? So maybe you got to spend like a third of your time or quarter of your time to actually solve the computation problem here. So as your model grows more sophisticated, you're going to need more computation power, right, to drive down both the overfitting problem and also to be more precisely trained against the ever increasing data you're going to accumulate over the different historical periods. All right, so how do you evaluate your result here? This is very critical, right? So whenever you have a model, you are going to have a final say, like if the model is good or not. In the trading space is actually pretty difficult problem because every period is different, right? You have idiosyncrasies. You have period like last couple of months, which is very different from last couple of years. So it's very hard to evaluate the result. So, and also for a lot of experimentation, like you have so many different models, like some of it it's got to be good at some period. So it's really hard for you to pick out a single model at a single period of time and say, okay, this is good, right? So it's got to be a more sophisticated way of evaluations here. So let me go to the next page here. Is that what I usually do is that I will usually employ something called sensible visual structure. What I meant by that is actually you usually have to plot a lot of different graphs, right? And plot the output from different model against the different characteristic of the time we are talking about. So basically, let's say, right? Let's say you have many plots here, right? Each one is against a different time period, right? So maybe this is against a high volatility period, which is crazy period, and this one is against a quiet, like maybe a couple years ago when there's not much going on. And maybe you have another like high volume days. Maybe you have big cap, right? Small cap. So a number of graphs, maybe what you can plot here, maybe is the in-sample prediction result. Maybe this is a gauge of your what's the power of the model in the training period, in the in-sample test, right? So, and then maybe you need to plot is out sample efficacy, meaning how does this model, right, perform when you are giving this model new data that it hadn't seen in its training period, right? This is very important. And maybe this model stands here, or maybe this model stands here, right? And there going to be some structure emerged from here, right? Maybe you see some structure like this. And maybe you see slightly different structures here, right? So you have to make a judgment that is this a stable structure, or is this just a fluke in a big ocean of statistic, right? Is this artifact, or is this real? So this requires very deep domain knowledge, right? Because you only after you have played with so many different models, you will stand to gain insight what's actually important. So but coming back to the evaluation, it's what I would call this is a visual process. And only after you are comfortable with a visual picture that you think there's structure involved, then you are going to compute a final number or a set of final numbers, which is pure deterministically computed without the visual aid, without seeing. And those final numbers are going to guide your final decisions here. All right, so I think this sounds a little bit, I think this sounds a bit more involved, but I think we already passed the most meaty section. So I'm going to ask Sean to open up the mic, and if you will have any questions here.
Okay. All right. Anybody any questions?
他怎么知道？
All right, let me just, give a little bit of background about our discussion here for the people. I mean, a little bit late. What we are doing now is basically we have we have a weekly discussion. Basically, it's very informal. We're trying to because right now is a special time, right? It's have to be as
就去平行班了。
So we're going to have a weekly discussion, more laid back and amicable. You can ask any questions, you know. You don't have to be like so, you know, technical even, right?
Right. So maybe let's do this. Can you guys hear me?
Yeah, I can hear you.
All right. So maybe I think I just got maybe 5 minutes to go to wrap up the trading system here, and then we can have the another casual discussion here. So let me wrap up. I think it's going to be quick, like 5 minutes here. We're running a little bit late here.
Okay, should I mute all? Or?
Yeah, you can go ahead and mute more, and then we start the final sections here.
Okay.
So you came up with a fantastic model, and you're very sure that it makes sense. It has a reasonable theoretical explanation of how and where the profit is coming. And how do you go about putting up the whole end-to-end trading system to realize the profit? So the first thing I can talk about is that we need to, other than the research on the forecast of the prices, there's a whole another subject, another science of how to determine how to forecast the cost of trading, right? So that's a big piece, but I think so contrary to the forecasting of the prices, I think there's a lot of literature, articles or papers about the guesstimate of the cost of trading. So sometimes people will call this like market impact model or TCA, different names, but it's a big subject here. But I'm going to skip this part because this is usually sort of universal and commoditized. So once you have the alpha projection model, which is a price forecasting model, and the transaction model, which takes care of the cost part, right? You're going to have a portfolio being constructed, right? So this is again a optimization problem, a well-defined problem, right? A quadratic actually optimization problem, which can be solved by a lot of commodity software. So once you have the portfolio constructed, you're going to have all the signals going into the portfolio, as well as all the estimated costs of some trades. Then what the portfolio is going to output are trades, or the trades are going to do in the next interval. Okay, so that's the portfolio construction. Then once you have that, then you can go about trading model, right? So you're going to build. So let me write. You're going to build the market data, right? A piece to a feed handler, which is going to decode the market data, right? So those are like prices, volumes, other stuff, right? And this is going to produce a big matrix we just talked about, which is going to go into your neural model. This is a neural network, right? And this is going to output some alpha, or what I thought about is price forecasting. And this one go to the portfolio, which you talk about, right? And a separate piece, which is the transaction cost, right? So this is a cost. This is also go to the portfolio, right? The portfolio is going to give you, right, what portfolio to buy, maybe IBM, maybe sell Microsoft, right? And this is your trades, right? So, and you have another whole piece of here, which is the order placement, right? So the order placement is going to take the trades and take the market data, right? And this is actually going to do either one of the following. They will post orders onto the order book, right? Or they will try to aggressively, so this is passive, right? Passive laying orders onto the book. Or you quite aggressively, you can take out orders on the other side. You can buy and then reach out to buy. You can sell and then reach out over the spread to sell, right? And then once you have the trades down here, you're going to get execution report, right? So execution reports, right? So this execution report is going to come in, again, going back to portfolio. This is going to update your positions of Microsoft, of IBM, right? And then the cycle goes on and on. So it's pretty complex system, pretty involved actually. All right, so that's this one. I'm just and the next one is actually it's my way of trying to say that you don't really want to build the whole thing and then try to optimize, right? You should really do a piecemeal. Maybe you just build the order placement part first, right? And then you can try some dummy trees here. Just give some test trees. Then you'll be able to figure out this chain is working correctly, right? Then the next one, maybe you build the feed handler and then trying to make sure this part is correct. Then to test this one, you just have to make this into a separate environment and test it separately. And you optimize piecemeal, so you don't just swallow everything at once, because once you do that, it becomes extremely difficult and involved to debug anything. All right, so I think the final 2 slides are actually talk about what's going to happen in the future. Like, so very soon, I think the model is going to be any model, right? Once it's becoming very profitable, there's people taking the model to different places, right? So it's going to be commoditized very rapidly. And there's now a big focus on trying to feed alternative data in real time into the portfolio, right? As additional unstructured data source. Very exciting, but also this is also rapidly becoming commoditized. And there's big debate about maybe what people should be doing is combine the discretionary trading with the quantitative trading, right? There's quantimental. There's people thinking about we should insert some human into the loop of the system, right? And finally, there's once we have commoditized model, it's becoming a game of speed and low latency. So it requires hardware acceleration, which is actually very technical. People are building specialized hardware, maybe FPGA, maybe ASICs to help speed up the trading here. All right, I think this one is this is final slide here is there's also other development here is that there's also a lot of people are researching in space for reinforcement learning, right? So this is more like trying to give the program reward and a penalty, like at certain predefined steps, right? So it's a pretty active research in this space. And then we're talking about how do you scale up the operations through. So typically, if everything else is commoditized, and people are talking about scale up the system to beat up the smaller guys. The way of doing that is by integration with risk, right? There's several ways to do that. Maybe it's cross asset. Maybe by trading in different assets, you're going to have correlation being like against each other. You are going to have much smooth return, right? There's also integration with risk by trading in many different global locations, right? Different markets, right? Also, there's also integration with risk by like trying to hold up the position, maybe not shorter but longer, right? So by maybe you can tolerate a much build up of the position. Maybe you can earn more money if you are going to take a little bit more temporary risk, right? So ultimately, I think there's also another piece of ethical problem here. When the program is getting smart, right? Maybe the program will come up something equivalent of spoofing, right? It's very possible because the program, by doing reinforcement learning, it will sooner or later come to a conclusion that if it's going to try to sell, it may try to spoof in some of the order on the bidding side. So it's going to happen, and how do we deal with those regulatory issues once we have those ethical problem, ethical dilemma within those arithmetic trading algorithms and systems? I think that's it. So that's the end of the presentation. Anybody have questions here? So Sean, can you open up the mic?
Open up.
How do you evaluate alpha?
Sorry, I think it's very background noise. So can you repeat the questions again?
How do you evaluate alpha from the signal you generated?
So the alpha, so the ultimate judge of the alpha is basically you're going to calculate, like in the simulation or by practicing real trees, right? You're going to have. So Sean, can you maybe mute everybody?
Okay, yeah, this reminds me of this Supreme Court. They have this thing too. So.
All right, so yeah, I think it's.
All right. Okay.
Okay, so evaluation of the alpha is usually done by calculating a number of matrix, right? You have the sharp ratio, but it's not the ultimate determinator because you would rather trade at a much increased capacity, even if it meant like lower sharp ratio, right? Because you're going to make more money. So that's one way to view it. But in a more narrow and a more definite way of evaluating your alpha is that you can restrict the problem to the problem of pure at the model space, right? You don't enlarge this thing all the way to the systematic space. Like within the much narrow definition of the model research space, then your alpha can be evaluated by standard practice such as correlation when given out sample data. And that's actually a pretty difficult subject because the time series in sample out sample is rather tricky. And especially given that you have very different regimes, right? How do you structure, how do you strengthen how do you structure your in-sample, out-sample? And that's actually a very different subject. But I think that's give you a flavor of what's actually been done.
Let's say, thank you. So let's say, suppose you generate some signals, I generate some signals. Your signal is very strong and my signal is weak. So when we have the final performance, how do you just evaluate the strengths of individual signals?
Right. So first one when people add up different signal, right? It really depends if those signals are correlated or those signal alpha are orthogonal. If your signal is weak, meaning if you have a small correlation number, but if it's uncorrelated to the big main signal, it's going to be added up anyway, maybe by a much smaller weight, right? That's in the stage of portfolio constructions here. But in terms of final, like the judgment is basically, let's say hypothetically speaking, let's say we put up those two signals over there, right? We run some of the, we pilot some trading, right? For each individual trees, right? You're gonna have attributes associated with those trees, right? So from backtracking those parameters, you will be able to see which signal is active or which signal is benefits to certain profits. So you basically have profit attribution system, which will tell you what profit coming out of each signals. So again, that's actually it's simply said, but it's actually pretty complex process here. All right, anybody else?
I have a question.
Sure.
As a individual person, where to get the data for simulation?
So I think it's the market data. You can probably grab those market data, like from open source. I think they do have some shared data. I think but for better quality data, I think usually people, you have to buy from exchange or you have to buy from vendor. Some people would do this maybe in certain managed vendor frameworks such as Quanta API. Maybe another source is that you can grab this data, like there's always sample data from the exchange, so maybe you can grab those data as well.
Okay,
but there's no free lunch here, meaning there's